Overview of the fundamentals of series and parallel elements. Kirchhoff's laws are the governing laws of circuits. All techniques are derived from Kirchhoff's laws. Now, there's a little issue with inductors because inductors require Faraday's law, but Faraday's law appears to be different than KVL. But if you use the strict KVL from circuit theory, then Faraday's law falls into it. However, the way it's taught is that KVL and Faraday's laws are actually separated. The techniques of resistor reduction is what I personally call simple circuits. Since no advance circuit theorems are employed. So one example is that we don't use like node or mesh. So in this chapter, the focus is only to identify what is in series, parallel, and then apply resistor reduction. Now note, even though I say resistor reduction, reduction techniques also simplify sources. If circuits cannot be reduced, maybe it's cannot, that's going to be the big word. Be reduced via reduction, then they are not simple, since they are unsolvable with these techniques. We break up this chapter into two parts. So one, we have circuits that only have independent sources. So here, one must identify which group of elements is series or parallel. This process is intuitively very important since one builds circuit intuition. Two, both independent and dependent sources. What we're going to find here is that the way these circuits are set up, one is required to use KVL, or maybe I should say and/or KCL, since these are not simple circuits. The idea is to set up two equations and two unknowns. Sometimes it's KVL and KCL, sometimes it's KVL and Ohm's law. It depends on the circuit. Let's move on to the fundamentals. So we're going to look at the fundamentals of series and parallel elements. So here are some important details. One, wires in a circuit are equipotentials. In other words, they form an equipotential surface. One assumes wires have no internal resistance. And from this assumption, the voltage across wires is 0. Because of this, voltage drop or voltage drops can only occur across elements. Three, power supplies and surface charges, in other words, charges embedded in wires create the correct electrical landscape that tells charges how to move. In other words, it maintains a potential height across the elements for charges to slide down its incline. And so if you look at the whole circuit, you have multiple inclines, and therefore those multiple inclines tell us what they do. As already stated, the fundamentals of series and parallel elements are independent of the element type. One does not care whether they're resistors, conductors, or capacitors, or whatever they are. So maybe I should write this here. The fundamentals of series and parallel is independent of element type. That is, one does not care if it's a resistor, capacitor, or inductor, or whatever. Their overall behavior is the same. So in other words, Resistance and inductors have a direct proportionality to length. Capacitors has a direct proportionality to area. Therefore, how we add them in series and parallel dictates how those add up together to identify whether elements are in series or parallel. One looks at the equipotentials. So when I say equipotentials from now on, I'm not going to say that. I'm going to call them nodes. So equipotentials on nodes are the same. So one looks at the nodes connecting elements together. So effectively, series and parallel configurations do the following. Series increases the effective length of an element. So in this case, we see that series resistors, they add. Series inductors, they add. Capacitors do not add in series because they don't depend linearly on length. On the other hand, parallel increases the effective area of an element. So when you look at adding elements in parallel, capacitance actually increases. Why? Because capacitance is dependent upon area, whereas resistance and inductance, they are inversely proportional to area. So adding more of them in parallel decreases their values. The result of this observation tells one how to add resistors, capacitors, and inductors in series or parallel. This is a huge conceptual jump that geometry tells us how elements behave as well as how voltages divide in series, but not in parallel, or how currents divide in parallel, but not in series. So now let's look at these individual series elements. So here we go. We're going to look at series circuit fundamentals. A series element have one common node between two elements. So if I have a wire and then I have one element connected to a second element like this, you're going to see that this guy, this element, is different from this element, and we'll call this element 1, and we'll call that element 2. How are these two elements connected? The way they are connected is we have one connection. This guy represents there's one node between two elements. So if I do that, then for a series circuit, the power supply in series with two elements behaves as follows. So let's just give a number to the voltage source. So what I'm going to say here is that I have a voltage source. And this voltage source, we're going to say is equal to 10 volts. So if I draw this circuit out, it tells me that I'm going to have two elements. So these two elements are the same elements as up above. And so again, this is element 1, this is element 2, and once again, this is our common node. That's our one common node between these two elements. So what do I see here? The first thing that I see is that I have an equipotential right here. And this equipotential, this is a 10-volt node. Since there must be a ground, then I could say that down here, this is my ground wire. And that means that right here, this is our 0 volt. So now if I go into my incline form, what I see here is that I have a 10-volt incline. So if I draw this, then I start to look at what are the charges doing here. So now, if I start to look at the details here, we can see here is that I have a node that's 10 volts here. And what we mean by 10 volts is that this guy represents the high. So if I place a charge on this circuit here, and let's say that I have this gray little positive charge, this positive charge is going to slide down my electrical incline. Now, if I look at this, you could see that this is one node right here. And then my ground node is still right here. And so what we see here is that what's happening to that charge. So any charge that's pushed up by the source, okay, any charge that's pushed up by the source, we are seeing charge moving down the incline. So here is my source voltage. And one of the things that I neglected to mention here is that that is the low potential. So what I'm seeing here is that we know that there is no buildup in charge on elements 1 and 2. That means that the charge going into 1 must also be the charge coming out of 1. Where else is the charge going to go? And then the charge going into 2 must also be the charge flowing out. So the source current only has one individual location that it could move through. So now the effective circuit, which is much more useful for us, now looks something like this. Since the incline produces an element that's that sets up an electrical height here, what we're seeing here is that this line right here is still my 10-volt equipotential. So if I'm looking at my elements, I see that as the current is coming down, by the way, I should label some other things first. This guy here tells me that this is the ground. This tells me that right here, I have my node right there. And so what we already know is that the source current comes out. It comes out of the power supply. And this is the source current. It then goes through 1. And what comes out of 1 is the current I1, but I1 is the same as the source current. And then the current I1 coming in is also the current I2 coming out because all of these three circuits are fixed. I mean, currents are fixed. So now what we're seeing here is that the voltage source, the 10-volt source, sets up the total height. So that means that since there is no voltage drop across wires, the only voltage drop that can occur is across the elements. So therefore, the electrical height across V1 is then going to be this V1. The height across element 2 is going to be V2. In other words, we have the same current and the voltages must be divided. So series characteristics means the following thing. They mean this. One, there is only one possible path for current flow. Therefore, all currents must be the same. In other words, I source has to be the same as I1, has to be the same as I2. 2. Voltages are always divided because wires don't have voltage drops. So voltages are always divided in series. So then that means we have no choice but to say that the voltage source must be the combination of V1 plus V2. That's what it means to be in series. So now the next one that we have to talk about is parallel. So now if we have parallel circuit fundamentals, we have very similar things as what we had with series. Parallel elements have two common nodes connecting both elements. Of course, we could have more than two. So if I look at this thing, then I see it something like this. So I have a wire coming in. And so then we have our elements. So once again, we have the same elements as before, 1 and 2. So the big difference here is that we have one node in red, and we have a second node in black. So what we're seeing here is that these two elements, they have two common nodes. For a parallel circuit, the power supply in parallel with two elements share the same two nodes. So picture-wise, it's got to look something like this here. We can draw them a couple of ways. So let's say that I have a source that looks like this. Let's say this is 10 volts. Now, if I come up here, I could imagine that I have a common node. So here's my node, elements 1 and 2. And as before, we identified this as the ground. So we'll continue to do that. And following the wire, that means that the ground is all along that wire. This guy, as we've identified this already, this is our 10 volt node. So we'll come over here and we'll write that this is 10 volts. The most common way that people draw this is that they come in here and say, okay, I have a 10 volt voltage source. And then they come in and they draw the elements like this. And you can tell that these two circuits are the same by just drawing the nodes. So these guys are exactly the same. So when I think about this as an effective circuit, the way we draw this here is that we could say that this is the effective circuit. So I'm going to skip the incline. So the effective circuit, we don't show the power supply, but we show them as node voltages. So in this case, we then say something like this. So once again, setting up my voltage sources, I could then say that here's my top node, and we know that this is 10 volts. Here's my ground, and we know that's 0. And then when I look at my voltage across my elements, we can see here is that each element has the same voltage drop across. We have no choice in the matter. So if I start to go in and I look at the parallel characteristics, then we have the following thing. One, voltages are not divided, but have the same voltage across parallel elements. In other words, if this height from here to here, if this is the source voltage, then that means here that this guy has a voltage V1, this one has a voltage V2, but because they all have the same height difference, then these voltages must be all the same. However, currents are always divided. So what do I mean by that? So if I start to look at current flow, let's say that I have current flow coming in here. And then what you're seeing here is that if this is the source now splits. And so this amount of current is now I1. This amount of current is I2, but we are dividing them. And then they recombine I1 and I2 so that what goes into the ground is the source. That being said here, currents are always divided between parallel elements. In other words, I source has to equal I1 plus I2.